I'd actually will just go and share this quickly in Twitter, although I have no idea what times of people are in anyway, whoever just want to watch me. What we're going to be doing today is we're going to be doing a bit more of the post selection stuff. Now, um, mm, I kind of realized that's going to be more complicated than I thought because I came across this example, which is, I think, a bit more canonical in terms of how hard this can be, right? So, and the example is like these. So you have this state, and you basically apply, just put the block series here, and you apply a Toffoli gate, right? And it's because it's an example of um, that I'm still kind of trying to work out a way to intuitively understand what happens with phase kickback here, right? Let me just uh, so chatting around, just I'm just going to tweet that chatting around, chatting about chatting about it to implement path selection on. So it's twitch.tv insert and says, is it insert? Yeah, exactly. Quantum computing. Awesome. Is this actually working? Let me see. Yeah. So Twitch tells me I'm live. Awesome. Perfect. Cool. Um, there you go. Yeah. Cool. So closing that up now, and I was thinking that I like path selection because I think path selection is a great tool to investigate or sort of kind of debug stuff because you can basically take literally kind of like imagine you've got branches, right? And you can literally just get rid of branches so you can see in a bigger setup where you cannot just see the full system. It's a bit of a, or if you want to zoom in, right? Like if you've got these and you want to zoom in into one specific branch, like path selection can help you do that. Although that might not just be the best way to approach this, but it's going to help you implement that. Because I'm thinking how could one use these hypergraph tool to sort of kind of support the development of algorithms or whatever. It doesn't even have to be algorithm. It's like I'm kind of I'm kind of really looking forward to the moment where it's not going to be so much about algorithms, but it's going to be a bit more about just coding stuff. And now I know that I found a bug here, but I'm kind of inclined to, and it's dangerous because I'm just spreading my attention too much, but I'm inclined to actually go back to the to the post selection function because I think it's not correctly implemented. I have the feeling it's not correctly implemented. And so I wanted to try and maybe build this example first. I don't know, does anyone know like what is, because I'm always curious, is anyone watching or whatnot, and I see here in OBS is someone called Lemon Jesus 12, and I don't know if this is a real person or because the Twitch app tells me that there are no viewers, and I almost don't want to click here. If I click here, yeah, I don't know, whatever. Anyway, if you're watching and you like what you're seeing, drop a comment, let me know. You know, subscribe to this thing or to the YouTube channel. I think it's always nice to see people supporting these, and it makes me feel good. Um, so what I was going to do now, exactly. So I'm basically back to this example, right? So it's let's try to see what we get if we build it here. So we have a hypergraph of 3 qubits, and we apply the, we apply these gates thing here and this gate here. So we've got this system. I don't have the Toffoli gate implemented, do I? No, but it's easy because it's these. Yeah. The Toffoli gate matrix. I think it's just with these things here flipped, or like this part here, right? So Toffoli gate matrix, I think. Yeah, exactly. That's what I'm looking for. This thing here. Okay, cool. This is actually an easy one to implement. So I'll just call it CCX, and it's basically this is the only difference. Okay, cool. And so what I do is I want to apply. First, let me just check that actually checks. Don't want to pause select anything. Okay, so I've got yeah, qubit 2 is in the minus state. I'm almost thinking like it would be cool to actually have a bit of a switch where you can actually switch to a more easy representation of the states. Like if it's a plus, it's a plus. If it's a minus, it's a minus. I think that would make it easier to read. Like, but if you just then want to take a look at the stuff inside, you know what I mean? Like, just change the labels. Like, if this is the label, I just want to see a minus. If this is the label, I just want to see a plus. And now we apply a Toffoli gate. So now I basically go ahead and say apply the Toffoli gate with these two qubits as controls. Oh, it's a 3-qubit gate, and I don't have that implemented. Ah, come on. Come on. But it should be kind of like the same, shouldn't it? Really similar. Yeah, that'd be actually, yeah, it'll be useful to be able to do that. But that's a lot of work now, so I think I'm not gonna go this way. And I don't want to implement the Toffoli gate decomposition because it's a lot of work as well. So we'll have to look for another example. Awesome. You see, my feeling here was though that I'm trying to think about another sort of a two qubit example where that would be easy to understand, or just a 3-qubit example as well. The thing here is if you pause select on minus, it kind of predetermines. Yeah, I should. The thing is, I'm really tempted to just say to go ahead and implement the sort of the generic controlled logic for these, whereas like I don't have to actually go and do the multiplication stuff, but I can just do the edge splitting idea, right? Where if you've got like your control qubit is, so you basically split your set of control qubits into all the possible combinations of zeros and ones, and then you apply the single qubit operation to the right edge, and then boom, that's it. Because that would make generic, you know, controlled operations. Like I could implement, whatever arbitrary large number of controls, and it would make things easier for these. Maybe that's what I should do, because it's going to make things easier. Because this is definitely a case worth studying, right? Because if I let me see if I can open Paint again, my favorite tool for painting. let's see what we would get here, right? So here we would get basically does this work? Yeah. So we start with a plus plus minus state, and then we apply the Toffoli gate, which and this is what I want to implement. I think in terms of a generic, because what I'm currently doing is for a 2-qubit operation, like a generic, you just give it a matrix and it just computes the local state vector between 2 qubits, and then it just expands the stuff. But there's a more efficient way to implement controlled operations in this scenario, which is like I'm just going to split branches, right? So I'm going to basically create like branches that look like these, right? And then here's all minus, and then here is a minus, but then here I apply the X gate, but this minus then kind of acquires a global phase, right? And so you've got a really efficient way, because I don't have to, like, I would have to compute the local state vector for the 3 qubits, which is 8 elements. And in this way, I can right away just create 4 branches. Yeah, which is actually turns out that this is definitely more efficient. So I think I'll just switch the topic to these, to be honest. Um, and I'll just get going implementing these. Makes more sense because it's going to allow me to do more things with Grover later on as well, and also then to have a good setup to play with pos selection. Because now the question I have is, so if I implement so if I want to implement this pos selection here, how do I do this, right? In my previous attempt, I was like, cool. So as long as they're not orthogonal, I just change each of the branches state to be a minus, and there you go. Like, I think that's what I was doing, which is, I think, really naive. Is it? I think. Uh, oh, and now I have a much better basis because I have splitting edges. So I have a bit of a functionality here that I can use to do the basics of splitting something in edges. I'm not sure how the amplitudes will work out, but maybe what I should do is maybe what I should do is the local product of these to get sort of to get actually the edges, and then I just add this guy inside. Of course, that's gonna make it super easy. I think. Oh, sorry for that. Let me see if I can. I don't wanna I don't wanna leave you deaf with my coughing. uh, but coffee is a must in the morning. And um, okay, so that's probably gonna be what I'll do because then now I I really don't know I really don't know how to like that's definitely not the way you would implement that, right? Because I what I would do intuitively is think, okay, so if I want to do a pos selection on mine of these minors, what I imagine doing is, well, it kind of means like in given this scenario, it means that like um, I'd have to have these merged, right? So I can merge the branches in a way that um, these two merge together or could merge together at least from this perspective because they are equal, right? So I could merge these together. And so I have a 0 plus and a minus, and these could merge together. And so I have a 1, a plus and a minus. But that's not correct because it's got this global phase that acquired, and when I do the merge, these actually pops up here, and so this is a minus. And so when I am doing pos selection now, it is clear to me that this goes away, and that's the only thing that I have left. And this matches with Quirk's results. But like in my previous implementation of these pos select, what I do is I go through the edges, and no, here I go through these and I just change the state. Yeah, if it is not orthogonal, that's just totally wrong. This is just really wrong. Mm. because essentially I'm flagging this as measured, and then I say I cannot merge that, and also that's not true. I can merge things. So that's just the pos selection is just crap. And I need to be able to build these examples in order to actually have a more useful working basis for these, because I cannot just merge this stuff, man. I just cannot. Okay, I could do these. Yeah. No, actually, maybe it does make sense because what it means is apply the proper transformation, like apply a Hadamard gate, and then pos select for 0, right? So that's what it probably means, right? It's not like I think I got it wrong. I think it's wrong in the sense that you cannot just give it any state. It's there's a measurement involved, and you can only measure in a computational basis, right? So you cannot just say pos like for these, right? Like it's always going to be the thing is it's going to be pos like z, right? And then it's going to be like um just pos like z, right? So uh, it turns everything to zeros or ones, I guess. It does it projects that. Or pos select x plus like 0 plus like 1 plus like plus like 1. I think that is because if I would just I'll accept any random state, like I'd have to basically calculate a transformation that takes me to that state as in that state being a basis, and then yeah, and then that makes no sense at all. That definitely makes no sense at all. So it's really what this is doing here is so I apply transformation to all these, right? And so I get like 0 plus minus 0 minus minus, and then 1 plus minus, and then 1 minus minus with this phase, global phase within this qubit. And so, okay, yeah. And so now it's telling me that, what? So if I now would do pos selection, I could get rid of these. I get rid of these, right? Now that's wrong because now my logic would tell me that, well, this merges, right? But this phase kind of gets now down to here. And so that would be minus minus minus, which is not the case. Okay, but it's an example worth working on. So yeah, this is definitely an example worth working on in terms of understanding pos selection. And I think that's gonna help me understand a lot more the topic in depth. But let's get to actually do the actual homework then, and let's work on a generic because I used to have that a version of that, but I left. I just dropped it because I didn't like it. I didn't like the way it looked like. So um, apply. So I want to take a version of these, I want to build a version of these, which is basically called like apply controlled operation, right? And so I give it the I give it the I give it the so I give it the controls, which are the sort of it's a sort of these will be an array of qubits, right? So control, is it control? Controls, this would be basically array of qubit labels. And then target, and then the gate, right? And so what this would do is, what this I imagine doing is, I think that it's got to do the same thing here, which is crap, but it's more generic. So, but it should, I think it should put all the control qubits and being in the same edges, right? Like, because that's the most generic case. And like, I apologize, because if you haven't been following until now, this all probably sounds like I'm just making that up. But when applying a 2-qubit gate in the most generic case, the control qubit doesn't have to be, in the same edge like the target qubit. So what I'm doing is I'm getting the edge IDs, and I'm saying if there's no intersection, then then basically merge things, like they put them into the same edge. No, okay. So I'm saying, okay, so if one of them is not in the same, right? So I think I have to basically loop over all the control qubits and execute the same code in relation to, like, the first qubit, for example, right? And then it says if both entangled but in different edges, we need to do some pre-processing as well. And then I do combine edges. I have no idea if these will really work. But from here, we assume both are either not entangled or in the same edges. And so then I kind of go and do the thing, right? And that's what I think we'll end up doing for a controlled operation, is a really similar structure, but I'll just compute the local state vector of the controlled qubits, create the edges, and then just how am I going to deal with a target qubit then? Am I just going to put it in there? Yeah. Let's see first if this works, okay? So if I can abstract that away, because then, to be honest, I think I can, yeah, I think this can all be part of one function that is like, how I would call this function. So that would be, what am I doing here? What I'm doing is I'm basically putting them, I'm kind of expanding them. Am I not? Yeah, I'm just basically saying, cool, you've got 2 qubits, just make sure they're expanded. So make sure they are in the same edges. I don't know. So, oh, we've got someone. So, what is quantum live programming? So, okay, so what I'm doing is, I don't know if you know about quantum computing, right? So in quantum computing, you basically, the idea is you program a quantum computer, right, or a QPU, a quantum processing unit. So what I'm currently working on, this project, is a prototype for a simulator. So it's not really programming a quantum computer itself, but basically simulating one. You've got a bunch of simulators out there, like Quirk, for example, here, right, which is just a graphical interface where you just drag and drop quantum gates. And like, I don't know how familiar you are with quantum computing, but like you program this kind of stuff in here, and then you can see how your state vector, which is the state of your system, evolves. And that's kind of a nice graphical way to work with these stuff. But it's really, quantum computing is hard in terms of it's hard to have a good intuition about what you're doing and what you're programming. And this is really low level, right? You have qubits, which are sort of the analog of beats in classical computing. And so you kind of build these really low level circuits with, something you can compare like ants and knots and stuff like that. And as you want to go up in terms of abstraction, you want to have a a more intuitive way to understand what's happening here. So I'm kind of working on a simulator that is different than the standard stuff you find in the industry. Usually you find simulators like, I mean, if you just go to Qiskit, for example, which is basically the library for quantum computing from IBM, like you've got a bunch of different simulators in here that are based on different mathematical models, right? The most basic one is just a state vector simulator. So what you're doing here is you're just keeping track of all these elements in here, and you see how they evolve over time. The problem with quantum computing is that the amount of elements you have to keep track of grows exponentially with the amount of qubits. So if you have, like 3 qubits, then you have 8 elements in here. It's 2 to the power of 3. And so it becomes really quickly intractable just because it explodes exponentially. And so, yeah, but what I'm trying to do here is I'm trying to kind of build a simulator that is a bit different. What it does is, instead of keeping track of all these numbers, it keeps track of the individual states of each qubit, which is sort of an exponential save in terms of memory needed. And then I try to keep track of the correlations between these, because you can do that's sort of another. Yeah, I'm realizing I'm just dumping into you all this stuff about quantum computing, which is probably, I don't know if you wanted to hear about this, and it's just really messy and unstructured. But the idea is you can entangle qubits, right? So you can do something like these, which is you put this qubit into superposition. So basically, this qubit is now somewhere in between 0 and 1, right, in terms of its value. And we don't know until we measure. And then you can do a control knot, which basically says, if this qubit is 0, then flip the bit in this other qubit. If it's 1, 0, don't flip it. If it's 1, flip it. So you end up with a state where it's really, there's a correlation. Like if this qubit is going to be measured to be 1, we know the control will also be 1. And if it's 0, we know this is going to be 0 as well. So there's a bit of a correlation here you have to keep track as well, because you cannot keep track of the separate states now. In this case, they are, you can see here in this block sphere, which is a display of the state of this individual qubit, that they are not, like, you cannot individually separate them mathematically, and because they depend from one on the other. And so what I'm building is, I'm building a simulator that basically kind of keeps track of these in a different way. So you keep track of the state of the single qubits, and then you keep track of the correlations by having different branches, different hyperedges in this hypergraph. And that is not, it's not to say that this is going to be way more efficient, but it's a project that helps me kind of gain a bit more intuition about quantum computing, and it has done already a lot positive for me in terms of understanding some of the low-level effects like phase kickback and stuff like that. But yeah, this is probably too much information for you right now if you're not if you haven't heard about quantum computing before. So this is what I'm doing in this channel. Live programming, in the sense that I'm not preparing for this stuff. It's really just live programming sessions on quantum related stuff. And sometimes I'll be doing some actual quantum computing programming. In this case, it's more of a simulator work. So it's a classical program, it's a traditional program, but I'm really just working on the simulator. Hope that helped. And now I got lost, but it's no problem. Where was I? Yeah, no problem, man. All good. All good. I like being distracted. It helps me think about all the stuff that I'm doing. And to be honest, And to be honest, it's I should do a bit of a recap at some point for people who are watching, people who might be new and just jumping into these videos. I've got a whole YouTube channel, by the way, where I keep like track, or I keep sort of an archive of all these videos and other stuff. So if you go to YouTube and you search for uncertain systems, you'll see these is basically my channel. And so there's a quantum computing 0 to 1. It's like it's material of war. It's material which is like, I think it's almost 2 years of worth material of me learning quantum computing, literally from scratch. So you can actually follow my process. They all these videos are really live stream like in terms of the format, and actually you can check as back to 2019. This is when I started, and then there's all the logs, all the video log sessions in here. So so this is actually D-Wave, quantum annealing, Q-Sharp, which is from Microsoft, and stuff like that. There's a lot of videos that I'm playing with here. And then I started
Let's give it another
I
try.
switched away
Okay,
from
let's give it another try.
YouTube recently because I realized that that was a bit of a closure for me, going from 0 to 1, having a basic understanding of what quantum computing is, and now I'm moving on to a more real life kind of project with building this simulator. And so I kind of ended up splitting these and having the EHS prototype video work logs, which is what I'm working on now. And this is where you'll find all the logs of sort of these project here. It's a lot of material, but it's definitely fun to watch. And now what I'm doing is I'm kind of streaming on Twitch and then putting things back to the channel as well. So this is probably now we're like 25 videos or something like that. Yeah, when I started. Oh, that's badly classified. That shouldn't be here. Anyway, yeah. So that's just for a bit of background. And I think I should basically do a bit of a stream soon where I maybe kind of step a little bit back and outline the whole idea of the simulator, because I think it's an interesting piece of work. And it definitely comes with some gains in terms of efficiency, if you think about other simulators in the industry. But I'm not claiming this is going to be something that allows you to simulate like 100 qubits or something, but it's definitely something that is better than just the brute force way of keeping track of all these values, right? And in particular, I'm currently working on being able to implement 2-qubit gates, so gates that interact, not 2-qubit, but like multi-qubit gates, which are gates that apply across multiple qubits instead of just single qubit boxes like this one. And so, yeah, basically that's what I'm currently doing. Apply. And I have a bit of an idea of how to do this, because I think that the the way the 2-qubit gates are implemented, right, is basically I'm just cheating, right, because I'm doing a bit of a brute force thing. So I'm actually computing the 4 values, and then I'm applying, and then what I'm doing is I'm actually trying to factor out and build the correlation hyperedges from there, which is a bit cheating because that's what kind of kills performance. I have a 3-qubit, if I have a 3-qubit gate like this one here, and I want to implement a 3-qubit gate following this method, I need to compute the 8 elements, right? Which is just stupid, because then it's just like, I mean, that's kind of where I kill the performance, right? Because if instead of 3 qubits, I'm talking about like a 5 or a 6-qubit gate, then yeah, it kind of sucks. Now, there's one thing I can't avoid, which is that I cannot know in advance, I think, how many correlations I will be able to factor out of these. So if the operation is a controlled operation, I know that these 2 qubits are not going to be affected by the gate itself, but I know that they at least, or at most, create 2 to the power of 2 in this case, because 2 control qubits, different hyperedges that I can then factor out. And so I think that a smart way to implement a generic control gate, which is not just, there are more types of control gates there, of 3-qubit gates, but like control gates are a specific subcase that I think can be implemented quite optimally, which is, or a bit more optimally, which is basically if I just if I just create the hyper edges that I know I need in the worst case, and then somehow I push in the target qubit in there and apply that single matrix multiplication, I should be good to go. And maybe there's a more efficient way to do that. Maybe there's a more efficient way to do that. But that's I think for the purpose of these, that's probably the best way forward. Just because I need to be able to implement, I need to be able to run 3-qubit operations so that I can debug and I can actually practice more complicated cases of the post-selection gate or the post-selection concept, which is the idea that you measure all the qubits at the end, and then you'll just pick a subset of your results, and that determines how the rest of the state looks like, which is a really useful concept for playing around with algorithms and debugging and stuff like these. But I need to do that because I don't understand. I don't have the right intuition for these. Like, mathematically, you can work that out. You can just, this has this sort of a mathematical matrix representation to it. And, it's somehow like, yeah, you can just multiply the whole stuff, the whole matrix of your state vector by this element, and then you get the result that you want. But that's like brute force. And I'm trying to have a more of a non-mathematical understanding of what's happening behind all these, which is what's complicated. Like if you ask anyone in the industry, or even just whoever in Twitter, like people are just like, just shut up and calculate, right? So you can of course calculate stuff mathematically, but that's not fun. At least it's not fun enough for me. So anyway, now, and I promise I will do a, maybe I'll just do that next maybe tomorrow or on Wednesday, because I'm planning to stream a bit more this week. So the next stream I think should be a bit of a step back and presentation of the idea. I think it's going to help me as well to see if I'm sort of on the right path. But what I'm trying to do now is I'm trying to say, okay, how do I compute? How can I compute these two? I've got a generic set of qubits that are my control set qubits, and I want to compute. I know that I know this is going to generate at most 2 to the power of that number of edges. So how can I compute those edges? And I think the right term for these would be really to expand. I think this is it's sort of the opposite of factoring, mathematically speaking, right? So I've got 2 qubits, and I want to just calculate what's their expanded state vector, which is a function that I had written somewhere here as a to-do actually. Yeah, expand. So I think I can just give it 2 qubits, because then I'll just, you can expand 3, 4, 5 by just doing this iteratively, which is probably not maybe the most efficient, but oh, sorry. That's not what I meant. I meant expand in here. So I'll just give it, actually, it's not any number of qubits. It's actually 2 qubits, because that makes it easy. And it is actually, apply to it is the first, it's really, I think, this first part of the apply 2 qubit gate, where not only the first part, but I think it's everything. No, it's the first part. I'm expanding it, and then what this is doing is it's going through the nodes and applying the gate. Yeah, it's these. Yeah. Okay. Actually, I can easily re-implement that by just saying uh, it's these with the identity gate. I just realized now um, that's what it is. It might not be the most efficient, but it's probably the quickest way to get there. So because the identity gate does nothing to it. So basically, if I have a gate that I just that's it's a bit cheating, right? But so I'll just call it II. I don't think if this is the right way to call things, but so it's a gate that does nothing to it. It's the identity matrix for 2 qubits. So just leave stuff untouched. So literally what I can do is for expand qubits, I can just go and say, well, self apply 2 qubit operation. Um, keep forgetting the names of my functions. 2 qubit gate. Okay. Um, expand 2 qubit gate ABII. So this actually, what this should do is it basically puts. Okay, but I cannot now. But how do I expand 3 qubits? That's the good question. How do I expand 3 qubits? Um, oh God. What I should do now is I should expand, because that expands 2 qubits, but it does not give me. That's not what it does not take me to a place where it makes it easy to work with these iteratively, right? Like I cannot go and say, look, now comes the third qubit, and I'm going to expand it in there as well. Mm. Yeah, because if so, then I could just use the same function for what I'm trying to do. So that just makes no sense. That just kind of makes no sense. But it is. Let me think. Let me think. So I've got. So we've got 3 qubits, right? So we've got 3 qubits. You know, whatever. I mean, let's do plus and plus and plus, right? So if I expand it 2, I know this is going to be expanded into the 4 possible combinations. And now, oh, uh, would it work if I now would just say I don't really care about efficiency. I just want to get this done quickly, just so I can move on to test other stuff. Um, if I now say, yeah, if I now say expand with these, I think what the algorithm is going to do is going to put it in here. So it's going to say 0, 0 plus and 1. Oh, no, no, no. Okay, cool. I think that's going to work. I think that can work. I think that I've implemented this correctly. Um, yeah, 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 yeah. Because I had to do that because of the way entanglement. Yeah. Okay, let's try. So let's say this is what expand qubits look like, right? Hopefully I haven't messed up with anything. So what let's just try one dummy example. So we've got a system with 3 qubits, and I'm gonna put the system into a well-known state, which is basically the all Hadamard states. And I know that if I draw the system, I get the same that I have below. which is basically these. And I know this should expand into like all the possible combinations of zeros and ones of these three qubits, right? So it should expand into 8 elements. If I do system expand qubits and I do like this, what's going to happen? Boom, it's going to break. Why? Uh, hmm. Should work. Why doesn't it work? It's a 2 qubit gate. Oh, sorry. I've made it too much of this is too big. That's wrong. That's if it will be a 3 qubit gate. This is what I need. Sorry. I need it as a 2 qubit gate, so that's why it's not working and it's complaining about the dimensions. Oh, cool. There you go. So now you have, so now, we had 3 blue edges. Now we have, this is expanded it to 0, 1, like this is 0, 0, 0, 1, 1, 0, 1, 1. And if I do now Q1, Q2, will that work, please? Yeah, that worked. Oh, cool. Awesome. Okay, so I don't have to do, this is making it easy. Now, I've expanded the controls, and I like because it just does all the work for me. It actually computes correctly all the stuff that I'm factoring out. That's pretty cool. That's awesome. So okay, so now I'm missing one little piece though, which is, so how do I now say, um, how do I now say like this is for my control system, right? So for my controlled set, and I want to add this one, and I want to do a apply control identity on this one. Yeah, that's probably what I should just do this. I think that's yeah, it's just another, and then I just apply that gate. That is surprisingly easy, is it? Like, is that correct? That would be pretty cool. Although I think a bit inefficient, but it's a prototype, who cares? I'll just make it more efficient later. But it just proves that it works. If I now want to apply, wait a second. So I now expand qubits. No, so I've already expanded the qubits, and now I just say system apply gate. um, you know, yeah, well, it's just apply gate qubit 2 x. And let me print the state vector because that's gonna make it, that's what's gonna make a difference. Because I think it actually has worked. I think it's actually worked. If I print the state vector, which the state vector is basically, um, yeah, I'm just amazed at it. I just came up with this on the fly, and it actually seems to work. Uh, no, no, that definitely doesn't work. Oh no, wait a second, it does work. Or not, does it? Uh, I think it does. I mean, let's see if I can have a better example. Um, so, uh, okay, yeah, well, of course, it's all, so that works. But for example, how could I implement something like this? Can I implement something like this? I cannot. Okay, that's what makes it complicated, probably. How would I do that? Because now I would have to control that on that specific set. Mm, wait a second. What does it mean? So if I do like these, it means that, for example, these states are invalid, right? Because they would like there has to be a way there has to be a way to hack my way towards implementing these easily. Like I could now say I could now just say get rid of the edges that have invalid solutions, right? Um, or it's like if I'm doing a control node, like I know that I just have to get rid of all the edges which are not like which don't have a a 1 1. Yeah, that's probably the way that I should do these. So expand qubits. So apply controlled operation. That's the generic one. So what I should do here is I should basically say, look, what am I doing? So for qubit in controls, right? Self expand qubits, and so I say, you know, first qubit. First qubit is basically control 0, right? Control 0, first qubit. So I don't know. I'm not good enough with Python that I can do this more in an efficient way. But if I enumerate these and again the index and the qubit, I guess I can say if index. It's really dirty though. But I'm just a dirty programmer. What can I do about it? Index bigger than 0, then what I can do is self apply, expand qubits, and I do controls index -1, controls index, right? And so now that that expanded everything, and so now it's basically the same if I do at the end just like I do like self expand qubits, and I expand the target qubit with the first qubit, right? Yeah. But now, of course, what I need to do is self apply gate to the target qubit, this gate, and now I need to purge the useless branches. Like that does not, I can do that approach because I already have to have at least to the power of n different branches. Like I cannot like I cannot work around that. Um, because I need to work out all the amplitudes. Maybe there's a smarter way to do that. Uh, hmm, hmm. I have to think about it if there's a smarter way to do this. That works, but there must be a way where I can do the expansion a bit more smartly, especially if I know that all I care. No, something's wrong. Like, why do I have to purge? Oh yeah, I got to purge for the invalid states, right? Because when, like, this is just an invalid state. It means I cannot have. Yeah, but I want to have this one. Like I. Oh, okay. Yeah. Maybe yeah, I got to purge the invalid state because basically, I cannot have a one, like if the two control qubits are not one. But what is the smarter way to do that? But yeah, I can just purge the invalid states. That's like, yeah, that's a to do. I'll drop it here. I think I have to step back a little bit and do a bit of a kind of like checkpoint stream, and kind of talk a little bit about the idea more in depth. But I think that's not a bad idea. So then I purge the yeah, I just purge the invalid. So I just basically I need to purge, but it's easy, right? I need to go through all the edges, and those who are like, yeah, if there's no like a 1 1 1 1, then I you know just purge them, just kill them. But then how do the amplitudes, then I need to adapt the amplitudes correspondingly. So let's make sure the not the amplitudes but the complex factors, edge factors, stay consistent. Cool. I'll leave it here, and I'll do probably I'll do a bit of a checkpoint the next day, tomorrow or the day after. But I like that. I like the fact that it's actually an easy way. You can expand to qubits by applying a controlled identity, and then I can just process the rest like that. And maybe there's even a smarter way to do that, which actually makes these more efficient than I thought it would be. Yeah, a bit more efficient anyway. Cool. I hope that was useful. I'm just running out of time now. Anyway, see you later.